Good morning. We are Group 16 and our presentation is on supersonic shockwaves. A sonic shockwave occurs when the air traveling around an object is near and above the speed of sound. As you can see in these examples, there is a visible cone surrounding both airplane and bullet. A shockwave can be heard as a sonic boom when the object accelerates past the speed of sound and is visible as a condensation cone as shown on the previous slide. This cone forms when the airflow velocity around the object is within 20% of the speed of sound. We formulated the hypothesis that, for an airplane, the resulting shock wave from a sonic boom breaks up into a turbulent wake. This is due to the compression of air in front of the plane piling up as the plane reaches the sound barrier. To determine whether our hypothesis was supported, we devised a realistic problem. For an F-16 fighter jet flying at 670 meters per second with an oblique shock angle of 60 degrees, find the corner angle and the final Mach speed m2. Will a condensation cone form and at which speed? And if the height of the wing is 10 centimeters, is the airflow turbulent? Condensation cones form when the downstream airflow velocity, also known as the downstream Mach speed, is within 20% of the speed of sound. Assume speed of sound is 340 meters per second and the specific heat for air is 1.398.
Here are the equations we use to solve this problem. First, we have the Mach equation, which uses the velocity of the object and the speed of sound to determine the Mach of the vehicle. Mach 1, therefore, would be when the object velocity equals the speed of sound. We also use the theta-beta Mach equation provided by nasa.gov to solve for the corner angle theta. Finally, we use the downstream Mach speed equation, also provided by nasa.gov, that is used to determine the speed of the airflow over the wing of the plane. We plugged in our given values to the Mach equation and calculated that the plane is traveling Mach 1.97, which is 1.97 times the speed of sound. Plugging in this value and our other givens into the theta-beta Mach equation, we calculated the corner angle to be 26.43 degrees. When we plugged in our two calculated values and our other givens into the downstream Mach speed equation, we got our final downstream velocity to be Mach 1.155. Plugging this speed back into the Mach equation, we find that the downstream velocity is 392.7 meters per second. We also calculated that the downstream velocity is 15.5% greater than the speed of sound. Since this is within 20% of the speed of sound, the cone of condensation will form. Finally, to determine if the wake is actually turbulent, we use the equation for Reynolds number. After plugging in our calculated velocity, given height, and standard values for air density and viscosity, we calculated Reynolds number to be much higher than the threshold of 2,000 to be considered a turbulent wave. Through these calculations, we have shown that the condensation cone will form, therefore supporting our hypothesis. In addition, we determined that the airflow around the airplane wing is turbulent, as the value of Reynolds number is over the threshold of transition from laminar to turbulent.